Hi everyone, my name is Jay, and in this last video I'm just going to be going over some math on Maxwell's and Faraday's law. So first is a line or contour integral. So a line integral is actually just for any general line, whereas a contour is just a closed line. In this example, I'm just using a closed circle, like so. And so what BDS actually means is you're breaking up this path into a bunch of little vectors, like this black thing here. So I'm breaking up the circle into a bunch of little black arrows, black vectors, ds. Okay, and what you're doing is you're doing a dot product between ds and b for every single one of those, and then adding those up. So that's the summation here, and that's what this integral means. And so, in general, for the line integral, because we're taking the dot product with each ds, we want to make the surface or the contour that we choose to be either the same direction or the 90 degrees as ds. And so if we know b points up, for example, then if we choose this square, right, it either points up, sideways, down, like that. And whenever we take the dot product, it's either 0 or just the magnitudes multiplied by each other. Because otherwise, in general, there's some non-zero theta, right? Where a dot b is a b sine theta, right? So in general, for any general contour, it might be hard to figure out. But if we choose a very specific one in which theta will always be 0 or 90, then we never have to worry about this, and we can just multiply those things and make this equal to b like dx without the vectors, and then just integral. The second one is flux, or a 2D integral. These are actually just interchangeable, and it's the same idea. So going a deal with the circle again, if b is a vector that's going into the page, for example, we're making the surface, whatever surface we're given, into a bunch of little areas, dA. So dA, like this. And the n hat direction, so dA is defined as n hat, the regular differential dA, is defined by the direction that you've chosen your contour integral. And so if you've chosen the contour integral to go that way, then positive by the right-hand rule will be this way. And so this is where n hat points. And so in general, this would actually be a bad choice, because then you'll get a negative sign. Because for each time you're doing b dot dA, there's a negative sign there. And so whenever you're saying flux, if b is increasing, then flux is decreasing, which is kind of hard to think about. So I always choose, if we know b is pointing into the page, I want to define a dA in the same n hat in the same direction. And so to do that, I do the contour integral that way, and then if b is increasing, then the flux is also increasing. It's easier to think about. But yeah, back to that. For circles, we do the normal r d theta, right? So that's r d theta dr, and that's your dA, and then your n hat makes it your vector, like that. So now, specifically with respect to Maxwell-Ampere's law, in this video, because we're talking about the math, I'm just going to be talking about the displacement current side. So this is d flux E dt. How these two integrals relate to each other. So in general, Maxwell-Ampere's law, you first have to know the direction or the shape of B before using this law. And you want, if you know the shape of B and you want to find the magnitude, then you can use this. So if you know that in general for a capacitor, right? So you have a capacitor like this. You know that the magnetic field is in a circle, but you don't know which direction. It's either that way or the other way. So I don't know, this way. We don't know. We can find out using Maxwell-Ampere's law. So first, you choose a direction that is positive. So you know that's in a circle. So if we, even if B was like this, right? The line integral, because we're breaking this up into a bunch of DS's, will actually just be the same as if we chose this one over here, except that it would just be negative. And so the negatives will actually work out, as you will see. And so if the magnetic field was this way, for example, in a circle around, like that, we know that BDS will be negative, right? So it'll be negative B and then 2 pi R, right? But on the other side, since we know that the left side is negative, we know that d phi e dt is also negative. And so what that means is that the flux is increasing in the negative direction, or it's decreasing, however you want to think about it. And so what that means is that B is also negative. And so either you can go, if you have information about B pointing clockwise, then you know that the electric flux is increasing into the page. You can also go from here to here, so you don't know where B points, but you know where, how flux is increasing. If you know flux is increasing into the page, you know the left side also has to be negative, and so it has to go against the direction of the contour integral. Same thing if you choose like this. If you know magnetic field goes around counterclockwise, then you know that the flux is increasing in the negative direction. Since positive is talking about into the board, then flux is increasing out of the page. And then the same thing with the negative. Faraday's law is similar, except down there's that negative, which is very important. And so if we choose the left one to be positive, for example, then let's say we know that E is going in a positive direction, and so the line integral is positive. We know that the positive equals a negative. Then this thing has to be a negative because, positive has to equal positive. And so the flux is increasing in the negative direction. And so it's increasing into the page. And then the same way, if we define this way to be positive, and we have E is going in the same direction, and so the line integral is negative. Because of this negative sign, we know that the flux, the magnetic flux, has to be increasing in a positive direction. And so because for this one we've defined positive to be inward, it is increasing into the page. Okay, that's all I wanted to say. This is my last video. Just good luck on your final.